Welcome to Physics 4C Optics Lectures number 1 on polarization. So the first thing that I want to talk about here is that we're going to look at light polarization, and when we look at light polarization, what we said here is that a characteristic of transverse waves is polarization. And the analogy that I will use here is that when we think about waves on a string, we know that these waves are polarized, and they can be polarized in one of 3 ways. And what you find here is that we want to talk about waves on a string, and if I set up my axes, we could do the following thing here. So the first one here is we could have something called vertical polarization. And when I look at vertical polarization, I imagine that I have a wave that's transverse, and that the wave has a plane, sort of like a sheet that's moving down along this direction. And when I look at the sheet here, there's a component that's going to be along the y direction, and if it is, we call that vertical polarization. So if I'm looking at this wave here, this wave is actually going up and down along only the y direction. And this is when the wave is moving in that direction. Now it becomes, drawing waves like this becomes, very cumbersome when we're starting to look at things. What we do here is that we define this in such a way that we use a vertical arrow where it's essentially telling us that it's oscillating from this peak amplitude to that lower trough amplitude. And so this is what we call vertical polarization. Now, the second kind of polarization that we could have, instead of it being vertical, it could be actually horizontal like this, so that the wave is actually oscillating along this plane here. So if I look at the second possibility, we call this horizontal polarization. And if I draw my axis again as before, where the wave is traveling along the x direction, so the z plane is where that wave is oscillating. So if I look at that wave, this wave is only along the z plane here. And clearly this one's much more harder to visualize, but the way we'll do this here to make it easier here is that this wave, the way I should draw it is that I should draw it like this, but this is very, very hard to see. So what we'll do here is we'll draw it like this, so that it's perpendicular to this guy right here. Oops, I should only draw one vector, excuse me. So we want to draw one, and this guy is perpendicular to this to show that this guy is horizontal. So this is what we call horizontal polarization. The third kind here is that I could have a mix of vertical and horizontal. And if you have a mix of vertical and horizontal, that's what we typically call unpolarized light when we're talking about, light. But if we're talking about waves on a string, it's typically called circular polarization. And I'll show you an image of this thing in a moment here. So if I have unpolarized light, or unpolarized waves, what we're seeing here is that in this scenario here, now this one's tricky to draw, so you'll have to bear with me. What I want to draw here is that I want to use two colors. So I want to look at the red wave, which is vertical. So if I draw that, here's my red wave. It's coming up like this and down. Now I need my blue wave that has to be in the z-axis. And so when I draw that, you're seeing that the wave comes out like this, and then it goes into the board, and then comes back, and then it's doing this type of thing. And you can see that this is very hard to visualize when you're actually seeing this. But if you look at this wave here, we imagine that this wave is moving in this direction, and because it has both of the components of the wave here, what we see here is that now we can draw this polarization as having part vertical, part horizontal, and this is what we defined as unpolarized waves. So we have vertically polarized waves, we have horizontally polarized waves, and we have unpolarized waves. Now, one of the characteristics of these waves here that is really useful is that you can filter out one of the polarizations if I have a particular type of a filter that can do that here. So what we can say here is that one feature of transverse waves is that one component of polarization can be removed or filtered. Or filtered out. And the way we do that is using a polarizer. So one image that you can imagine of a polarizer here is that you could imagine that I have the waves that are coming in as before. So if I look at this wave, my unfiltered or my unpolarized waves here, they're coming in like this. So you can imagine that I have a stream of waves going to the right. So if I have this stream of waves going to the right, as indicated by this wave speed v here, now imagine that I have a single vertical slit here. So when I look at this vertical slit, what I imagine here is that I have a hole in this scenario right here, and everything else is sort of like blocked out here. So as this wave comes through this vertical slit, you could imagine that there's a piece of the wave that's sort of going to slip through the vertical hole. But if the horizontal one tries to get through that hole, it's going to get blocked by this thing. And so what happens then is that you see that the only thing that comes through them is that you're going to get the only component coming through the polarizer is the vertical ones. The horizontal ones get filtered. Now this picture is a little bit abstract, but if we were to kind of draw this out, you could imagine that I have a wave that's sort of like coming through this thing. So to show you what I mean, there's an applet on Wikipedia that I want to show you here. So if I go to the applet on polarization, it's not an applet, excuse me, it's actually an image. This thing is moving in a circle. So you could imagine that you can have an X component and a vertical component. And what you're seeing here is that there's a horizontal gap, just like the filter that I showed on the board. But what you're seeing here is the only thing that's going to make it through is this horizontal component. Therefore, this is a polarizer for string waves. Only the motion that's along the slit direction actually gets through. So if you look at this thing here, you can see how this can filter out the horizontal component, but here I'm getting only the vertical component that's coming through here. So what I want to do here is that now I want to transition to electromagnetic waves. So by doing this, we need to go back and look what actually happens in electromagnetic waves. So, so now we want to talk about electromagnetic waves and polarization. The first thing I want to remind you is that I want to go back to the image of the electromagnetic wave. So let me bring this up. Is that right?
Yeah, I can see that.
And what you see here on this wave is that the red part here is the electric part. The blue part here is the magnetic part. And one of the things that we said here is that the only part of the field that in general deals with optical stuff, sort of like transparent mediums or microwaves, is that we find that the magnetic part does not contribute to the interaction between light and these materials here. So if only the electric part contributes, then that means that when I look at this wave, for example, the red part is the only thing that we pay attention to. And that red part is the electric field. So when we look at the polarization of a wave that's electromagnetic, we only focus on the electric part here. So that means here, I could then come back and talk about the three types of polarization that we talked about with electromagnetic waves. So I have vertical polarization, I have horizontal polarization, or I have unpolarized wave. So if I talk about this with electromagnetic waves here, then it goes something like this here. So what I'm going to find here is that only the E field part of the wave contributes to polarization. So when I'm looking at a wave and I'm seeing this wave that's coming in, I'm seeing that my electric wave is looking something like this. And what we're seeing here, if this is the electric part of the wave, we see that the wave is sort of like coming like this here. And so the way we define this wave is we look at the amplitude. So therefore, I will then draw the polarization of this wave by this amplitude, and this amplitude is written by E initial here. Now what we find here is that the intensity, which is equal to the brightness of the wave is equal to the amplitude squared. So when I look at the intensity, we write the intensity here as this guy squared right there, because that's the amplitude of this wave. Now note, this is a vector, okay? And because this is a vector, we need to pay attention to that. So now, I want to go in and look at the possible polarizations of an electromagnetic wave. And so, here we go. So the first thing I want to look at now is I want to look at vertically polarized light. So what do I focus on? I focus on this. But what we got to be sure of here is that I'm looking at this thing here. So here's my axis again. So I have my axis, and I'm moving along the x direction. So this is my y-axis, and this is my z-axis. So when I draw my wave, it's again doing this type of thing. So if I'm looking at this thing here, then that means that this guy, okay, this guy is then going to be written here. This wave is then going to be E initial Y. Why? Because it's vertically polarized along the Y direction. And then my wave here is going to be sine of kx minus omega t. So there's my wave. And so when I look at the amplitude of this thing, the amplitude of this guy is going to be E naught Y, telling me that this is then vertically polarized along this direction. So if I do the same thing along the the horizontal direction, I then have horizontally polarized light. And if I look at this, I set up my coordinate system as before, and like I did beforehand here, what you're seeing here is that I pay attention to the z-axis, not the y-axis. So when I'm looking at this wave is actually coming in like this, and then it goes into the board. And remember, this is very, very, very hard to visualize because this is going into the board. And so when I see this wave here, this wave has an amplitude in the z direction, the horizontal plane. And then my wave, as we talked about last time, is sine kx minus omega t. And the way we draw this guy here is that we're going to draw it vertically like this. And so its amplitude is 0z like that. Again, it's a vector amplitude. And then finally, we have this unpolarized light waves. And so when I look at this here, instead of drawing these things simultaneously, I'm just going to use the pictures here, is that I'm going to get a wave that looks like this, a second wave that looks like this. So this has amplitude E initial Y, this has amplitude E initial Z. So when I look at the full wave, it's a superposition of these waves. That looks like this here. So when I look at the amplitude of this wave, it's a vector amplitude, and this guy says that when I draw this, the amplitude in this case has to be a combination of both of these guys right here. So these are the three polarizations that I actually get for light here. So what I want to do here is that I want to deal with misconceptions about polarization. What we just saw here was a video that if I had a string that goes through a polarizer or a filter, the vertical component is the one that's parallel to this through the slit, is the one that gets through. When we move towards electromagnetic waves, that is not true. It's actually just the opposite. And there are textbooks that will tell you that this is exactly what happens with electromagnetic waves, but that's not correct. So I want to clean that mess up so that we deal with electromagnetic wave polarization properly. So let me erase the board, and then I'll explain what I mean by that. So I want to talk about misconceptions. On light polarization. So what I want you to think about here is that if I have an electromagnetic polarizer, let's say for light that's microwaves, that polarizer essentially looks like a barbecue grill. And what you want to look at here is that it goes something like this. I need to produce a source of waves. And I'm going to look at two situations here. So what I have here is that I have a microwave source. So this is going to be a source of vertically polarized microwaves. So this guy right here and this guy right here are producing vertically polarized light. So that means here, so when I look at this light, I'm seeing these polarized waves that are coming out vertically. And what we're going to do here is that we're going to take these microwaves and we're going to shine them through a set of grills here. So when I look at these grills, what you're going to see here is that to try to simplify the drawing of a polarizer, I'm going to use a rectangle like this. And if I have a grill-like situation, you can imagine that I have a series of lines here. And these series of lines represent parallel metal conductors. So what we're seeing here is that I have a series of parallel metal wires / grids. So I have, like I said, like a barbecue grill. And on this scenario here, instead of them being vertical, I'm going to make them horizontal here, like this. So what you're going to find here is that if I was to look at mechanical waves, you're going to find that the vertical one should go through these because the slits are parallel to the grid, whereas these guys should not go through here because they're going to be perpendicular to it. But it turns out with the electromagnetic waves, the opposite happens. So that means when light comes in here, after the polarizer, let's say that this is the initial light coming in here, and I'm going to call this polarizer number 1, just so that we can use this for notational purpose. What you're going to find here is that the light intensity after polarizer 1 is essentially 0. However, the light intensity after this horizontal polarizer, where the light is perpendicular, this intensity is effectively exactly the same as the initial intensity. And so what that means here is that if you actually do this, what you're seeing here is that if you're on this here, you get absorption of light here. And in this case here, you get transmission of light. So the polarizers that we have for electromagnetic waves are the opposite of what actually happens here. So if I was to look at the light coming after this thing, I would get this vertical light that's coming through. So to give you an image from my lecture notes, what you're seeing here is that behind the barbecue here, the grill, what you're seeing here is that I have the source on the back. And if I put this thing vertically right here, I don't know if you can see this here, but this tells us that the intensity is 0 right there. So that means vertical light coming through in here, gets absorbed. Whereas if I turn it horizontal, if you could see that little mark right there, it's at maximum intensity. So that means that the light coming in is going to be the light that's coming out. And so what you're finding here is that this is what actually happens with electromagnetic waves. So the question is, why does it happen? So now this is the explanation of what actually happens here. Remember that this vertical field is an electric field, and that electric field applies a force on the electrons in this grid system here. So what you find here is that the E field applies an electric force on the conducting electrons in the grids. So what you find here is this, that if I apply an electric force, that means electrons are accelerated. And if they accelerated, you create collisions along the long length of the grid system. So then what you get here is that electrons collide and create heat. So as the electrons collide and create heat, the light energy now turns into heat energy, and therefore the wave that was coming through gets absorbed by the polarizer. So in other words, the light energy is converted into heat energy, and so therefore there's no more light that's coming through. So in this case here, you get that heat energy or light energy is converted into heat energy. And it gets converted into heat energy, we then say absorption of light. So therefore, no light gets through. On the other hand, if I look at this vertically polarized light on this horizontal, the grid cannot move the electrons too much because the wires are thin enough that they're not going to be able to move very, very far here. So in this case here, the electrons do not move very far when the grid is horizontal. And this implies here that very little heat is generated. And because very little heat is generated, this is why I said that the intensity after the polarizer is almost equal to the intensity before the polarizer. So therefore, we get this transmission of light. And so that tells us that the polarization is just the opposite of what happens in mechanical waves. So what I want to do now is that I want to go in and I want to really explore the fact that the light that goes through the polarizer is the perpendicular component that's perpendicular to the polarizer. So I want to erase the rest of the board, and then I want to go in and I want to explore that fact on light here.